There we go. Okay, so of course, I'll write it over here on the board, just the notation, the integral, the S shape from A to B, f of x dx, is our major new thing as far as notation goes. And that's simply the area between the x-axis and that function. Below the x-axis is negative, above is positive. If the A and the B are backwards from right to left, and the opposite, the areas are opposite as far as what's positive, what's negative. So in section 5.1, we had two basic things we did. Be able to find formulas, find areas geometrically, triangles, rectangles, trapezoids, circles, and then be able to find areas with integral notation, like splitting up the integrals. The integral from 1 to 3 plus the integral from 3 to 5 is the same as the integral from 1 to 5. Or the integral of 2x plus 7, we could split up into the integral of 2x plus the integral of 7 and do them individually. Although, now that we've learned the bottom thing, fundamental theorem part 2, we wouldn't have to do that. I mean, we'll talk about that here in a little bit. Well, matter of fact, we can talk about it right now, I guess. So we had to jump around here a little bit. If I gave you this problem to do right here, I could give you this problem on the quiz tomorrow in two different ways. I could give you the directions of find this area, find or evaluate this integral geometrically. Which means I want a picture using geometry formulas. So you could graph this, right? We could graph 2x plus 7, which would be something that would go like this, right? Here would be 7. From 0 to 2, it would be a trapezoid, right? Agree with that? And so what would be that area? It would be 1/2. What would be the base here? 7. What would be the base here? 11. Put a 2 into the function. And then the height of the trapezoid? 2. So this would be an answer of 18, right? I suppose a person could split it up. This would be more work, but we have the rule that you could split this into this, right? So I could do 2x, which would be this, from 0 to 2, which would actually be a triangle. So that'd be 1/2. Base of the triangle is 2. What's the height of that triangle? 4. 1/2 times 8, that's 4. And then how do you do the area of 7? Wouldn't that be 14? The function y equals 7 would be here. The area from 0 to 2. That would be a 2 by 7. 2 by 7 rectangle, that would be 14. 4 plus 14 is 18, right? So that's what we did in section 1. So if I said evaluate this integral geometrically, that's what I'd be talking about, okay? But then we learned number 3, so we're jumping around here a little bit. We learned the fundamental theorem of calculus part 2, and so now we actually know that we can find this, and this was some of your homework today. What can we do to find this integral? Logan?
You would put b in for x?
Not yet. Well, we could, we don't put a 2 in for x yet. What do we got to do first? We got to do the antiderivative. Remember, the rule was the integral from a to b of little f of x dx is equal to big F of b minus big F of a. Big F means the antiderivative. So we've got to do the antiderivative of 2x, which would be what?
X squared plus
X squared, right? The antiderivative of 2x would be x squared. The antiderivative of 7, 7x. And then we're going to do that from 0 to 2, and I showed you that right bracket. If you use the right bracket, don't use the right bracket, doesn't matter. But we've got to do the antiderivative and then plug in the b, the 2, and then plug in the a, the 0. So if I plug a 2 into here, 2 squared is 4. 7 times 2 is 14, so that makes what, 18? That parentheses, minus, and now I'll plug my 0 in, 0 plus 0, oh, that's just 0. So I get 18 minus 0, aha, same answer, 18, right? Now what's the advantage of the red method versus the blue method? We don't need geometric shapes to do the red method. All we need is the antiderivative. And of course, that's the whole thing we spent a week figuring out. The aha, everybody clap and cheer, right? The whole area function antiderivative thing led us to that point. That was the idea. That the area can be found using the antiderivative. Okay? And so that's how we can do a problem like that. So if I give you this integral and say, evaluate this using the fundamental theorem of calculus, we're talking about part 2 then, and we're saying, do it that way. And then I could give you that problem, just say, evaluate this integral. And I don't care how you do it. Right? Now, fundamental theorem's better because it can work on all kinds of functions, right? Whereas geometrically only works on ones that are geometric. If that had been a parabola or a sine function or something like this, we couldn't even have done the blue method. Right? Wouldn't have made a geometric shape. So, as we review where we've been, we started out doing section 1, doing those areas like we did the blue way. Well, that led us into learning about the red method, which we're going to get into a lot more. So this quiz is going to have some of the red, some of that antiderivative, some of that fundamental theorem part 2. But we're going to do a lot more with antiderivatives in the next thing we do, and that's going to lead to our gateway test, right? That's the next quiz after tomorrow's is our gateway test. We're going to do a lot of work with antiderivatives because obviously they're pretty important. All right? I mean, we can't do these areas unless we can do antiderivatives. So we've got to be able to do them. So we've got to practice them, and that gateway test is going to be what we practice to get ready for that. Okay? But for tomorrow's quiz, there'll be some of possibly doing it the blue area. Or I might just give you a graph like this. I might just give you a piecewise function, say find that area like we did. Okay? So there's going to be some of that on the quiz, and then section 5.3 just showed that. That's all there is to section 5.3 really is fundamental theorem part 2. Now some of your homework in 5.3 was also kind of the same kind of stuff from 5.2, using this whole idea of antiderivatives. So let's talk about 5.2. We spent a lot of time in that section, but again, the whole point of all that stuff in 5.2 was to get us to 5.3, to get us to the fundamental theorem part 2. But there's a lot of important concepts in there. And so once we realize that the area function is the antiderivative, all the stuff we did with the chart comes into play, right? And all those questions about the chart and those kind of things. And there's going to be some of that on the quiz as well. Now, hopefully that's easy. I mean, that's old stuff. That's chapter 1, right? And chapter 2. So there's going to be some of that. And then the whole point of an area function. Okay? So let's, matter of fact, let's do that before we get into the homework. Let's do one of those kind of things. Let's do a problem that talks about an area function. So this was what we did in section 2. So we said big A of X, or A for area, but it could be big F, big G, whatever, it doesn't matter. And let's say it was the integral from 3 to X of X squared plus, now we'll make it an easy one. We won't get signs or any of that in there right now, but it could have. Well, they could. I'll tell you what. Let me change this. Let's change this. Let's do get it. Let's do something with a sum. Let's go. Let's go from pi to x. Let's do that. Now, I've already got a problem with what I wrote. Hopefully, as I wrote that, you guys were like freaking out. You can't have an x in there, right? Hopefully, that was really bothering you. Okay? like fingernails on a chalkboard, right? That has to be something else. If I have an x up in that right endpoint, and that's, of course, what we said. In this problem, this is just a number answer. This is a definite integral. This is a fixed piece of area, the area from 0 to 2, from 2 to 7, from number to another number. That's a fixed piece of area. That's a number answer. But when you write this, that is a function, because that's a bunch of different areas, from pi to here, and from pi to there, and from pi to there, right? It's a bunch of different areas because it's a different right endpoint. All right? So what I might ask is find a formula, find an equation for a of x. Okay, now we did this a couple different ways. Well, one way we did it was with trapezoids and stuff like that, but I told you would not have to do that, right? We're not going to have to do that because that only works for a very limited number of functions that have geometric shapes, so we're not going to do it. Okay? We're going to do it with what? Antiderivative, right? That's what the area function is, the antiderivative, right? That's what we found out. So we're going to do it with antiderivative. So there'd be two ways we could actually do this one. So I'm going to do it both ways. There are two different ways we can do this. Okay? Either one is perfectly fine. The first way we did it was just simply with doing an antiderivative. So what's the antiderivative of this? What's the antiderivative of cosine? Sine. Now, is it going to have a t in it or an x in it? It's going to have an x in it, right? It's got a t inside here. But once I do the antiderivative, it's going to have an x in it. Okay? What's the antiderivative of 6? 6x. And then plus some c. When you do an antiderivative, there's going to be a c of it. Okay, now wait a minute. Why didn't we do it a plus c when we did this antiderivative? Why didn't we put a plus c here when we did the antiderivative? Because we were going to subtract here, right? Fundamental theorem part 2, we were going to plug in here, we were going to subtract, so the c would subtract out anyway. So if there had been a plus c here and a plus c here, and then we subtracted, they did just subtract it, so I didn't need to put it. Okay, but here I do, because I'm doing something a little different. So I'm doing the antiderivative of this, but how do we figure out that c? We need an initial condition. Oh, we always get a free initial condition with something like this, don't we? We know that a of pi is 0. If you put a pi right there, the area from pi to pi is 0. There's no area from pi to pi, right? There's no width. So we know that. So we can plug pi into this, so we would get sine pi minus 6 pi plus c would equal 0. Right? So let's solve for c. What's sine of pi? 0. So this would be negative 6 pi plus c equals 0. So c would equal 6 pi. So my function would be sine x minus 6x plus 6 pi. That would be this function. Now, isn't that the antiderivative of what's inside there, right? We could test it by doing the derivative. The derivative of sine is cosine, sure enough. Derivative of 6x is 6, and then the 6 pi is just a constant, it would go away. So that's one way we could do it. Now, this one we haven't done. The second way we haven't done. That's how we were doing them the other day, right? We had done the geometric way of doing it, and then we said, but we could also just do this. Once we learned it was the antiderivative, right? And here, let me pull that up. So if I go back here to, let's see, I think it was this. Oh shoot, I don't have it. I thought I had one here where I had something done. I guess not. All right, never mind. All right, but we could look back at, in the old videos, and we would show that we did some of that. We did our trapezoid. We said, oh my God, that's the antiderivative. You're kidding me. 3/2 x squared plus 3x or something like that. And then we said, well, we could have just done the antiderivative with a plus c, take our free initial condition, plug it in, find the C, and away we go. But now we could use the fundamental theorem part 2 actually on this. Think about it. We could just do what we just got done doing over here on this page. We could do our antiderivative, plug the A and the B in, and subtract. Watch how this looks. We'll say, well, let's just do this antiderivative. So that antiderivative would be sine t. Now this time I'm actually going to put t. You could put x here, but you'll see what I'm going to do in a minute. So antiderivative cosine, what's the antiderivative of 6? 6x, so let's put 6t, and then I'm going to put that right bracket. You see what I mean? Just like I did the 0 and 2, now I could do the pi and the x. And you notice I didn't put a plus c. Why not put a plus c? Because they're going to subtract out, right? I'm just doing that fundamental theorem part 2. So now what do? We put an x in for the t. So this, what I like about doing it this way is it kind of shows you, oh yeah, that's why there's going to be an x in there. That's why over here there's an x in my final answer, not a t. Right? So I do this antiderivative, plug in an x, plug in a pi. Well, look what happens. Antiderivative sine is cosine. Plug in an x. Oh, wait, time out. No, I did it already. Time. Jeez, dummy. Do it. I already did the antiderivative. It's right there. So I'm going to plug in an x. So I got sine x minus 6x, right? So I just plugged in an x. And then minus, don't forget these parentheses, very important. And now I'm going to plug in a pi. Sine pi minus 6 pi, right? And what do I get? I get sine x minus 6x. And what happens here? Sine pi is 0, right? This would be minus a negative 6 pi, which would be plus 6 pi. See how we get the same thing? Now we get the same thing either way. So find a formula for this area function means do the antiderivative, plug in an x, plug in a pi, subtract them, because that's what fundamental theorem part 2 said to do. But the other way to do it is just say, oh, I know this is antiderivative, just put an antiderivative, but I know there's a plus c. It depends on this pi, whatever the left edge is the c. So that's my initial condition, so I know a of pi is 0, plug pi in, set equals 0, find the c. Either way, that's pretty slick. Right? And it kind of fits with what we're doing with definite in it. So you can kind of do it there. If that's what we wanted, if we wanted a formula for that. You know, sometimes we don't. Sometimes we don't care. Sometimes we just know it's the antiderivative. Like the problems you did with the chart. So let's take a look at that next. Let's go to the homework problem on page 321. Let's take a look at that. I'm talking about 51 through 56. Okay, so I think it is, I think I saved this somewhere. Oh shoot, maybe I don't have this one. I was hoping I did. Darn it. Okay, well, that's fine. So it looks like this. It's got a half circle, then it comes down here, then it goes up like so, then it goes like that, right? And it says big G is the integral from -3 to x of little f, and this is little f right here. And it says big H is the integral from 2 to x. So what is the only difference between big G and big H? The plus c, right? The initial condition, the left edge, that piece of area between -3 and 2. That's the only difference here, okay? And so big G and big H are both antiderivatives of little f. So this problem, it does not ask you anything about finding a formula. So the problem we just did, I said find a formula, so we did the antiderivative, whatever. We don't care about that here. All we care about is that big G and big H are antiderivatives of f. And how did I say you could show that real quickly? What could you write down that would tell you that G is the antiderivative of f? I think you should write that on your paper, right? When you see that, I think that's the first thing you ought to write down. That's telling you that, hey, the derivative of G is F. The derivative of H is F. So that's telling you G and H are the antiderivatives of F. Okay? And now you can answer all these questions. So when I talk about the quiz tomorrow and say that the chart stuff, right, this is what we're talking about. So there's going to be some problems like that. So these should be easy. Because once we understand this connection, this relationship, then all that stuff we know about the chart is there. Okay? So the chart would look like this. We'd have big G or big H, doesn't matter. Big G or big H, doesn't matter. And then here you'd have little f in the next line. So when this is 0, you got stationary point. When this is positive, you got increasing. When this is negative, you got decreasing, and so forth, so on. Right? That's what the chart would look like. So in 51, we already did that. In 52, where is big H increasing? Big H is increasing when little f is positive. So from here to that point, which is what? -3. And then from 1 to 5. This is -3 right here. Okay? -1 would be here in the middle of that circle. So where is big H increasing? It's when little f is positive above the x-axis. Been the same thing if they'd ask where is big G increasing. It's been the same thing, right? The same thing, because big G and big H are both antiderivatives. They're vertical shifts of one another, so they're increasing in all the same places. 53, why does big G have a local min at 1? Why? Maddie, why? Okay, let's remember on the midterm, some people lost points on local min problems because they didn't fully say it. So really say it with all the pieces. Did you say it is going?
Oh,
okay.
F is going from negative to positive.
So therefore, because G is going from, if little f is going from negative to positive, thank you. Big G is going from decreasing to increasing, decreasing to increasing. That's a local minimum. You've got to have that. On the quiz, if it says that question, number 53, why does G have a local minimum at x equals 1? It's because little f is going from negative to positive. Therefore, big G is going from decreasing to increasing. That's why it's a local minimum. Chart. It was on the midterm. We hadn't even learned about this. How could it have been on the midterm? Oh, yeah, we had learned about it, right? We hadn't learned about area. So once we understand that these two are the antiderivatives of f, then all that stuff in the chart is just there, right? But it doesn't make sense to talk about G increasing when the little f is this, unless we've made this connection here. We've got to make that connection. That's why we write that on our paper. Okay? Does big H have a local max at -3? Yes, same reasoning. Because little f changes from positive to negative, so big H is changing from increasing to decreasing. Where does big G have its minimum value? Now it goes from -5 to -2, so that's here. They're only talking about from here to here, right? -5 to -2. Where does big G have its minimum value? Caleb, what do you got? Why? That's if you go backwards. I'm not following you there. You're talking about area here. Are you talking about minimum or maximum? The minimum's at -5. Okay. I agree. But I'm not sure about your reasoning there. Now listen, let's talk about this from purely a chart. Forget area for a minute. Forget this. We know they're antiderivative, but forget area and all that. Just this is the derivative graph, right? Right? This is the derivative graph. Where's the minimum? Okay, so Caleb, try again. I agree with you, it's -5. Well, this is the derivative graph. So what's big G doing in the beginning here? Anybody?
It's increasing.
No,
Increasing.
it's increasing. This is little f. Little f is positive, right? Little f is above the x-axis. So what's big G? Increasing, right? So big G is increasing all this time, and then what's it doing here? Decreases a little bit, right? Now remember we had that problem on our midterm too, right? We had one very similar to this. And we didn't get all the points because there were some other issues involved, but here there's not. It's just increasing quite a bit and then decreasing a little bit. So big G's going up and it comes down a little bit. Does it go down enough to get as low as it was here? No. Okay, but that's not a great, a little bit, it increases a lot and then decreases a little bit. That's not a really good thing. So maybe we could talk about areas. So we could say, so couldn't we calculate this area, right? In other words, this area here is enough more than this little piece of area here. You know what I mean? That kind of thing. So we could say that it's increasing more and then decreasing a little bit. So the minimum is back here. Where's the maximum? At -3, where this local max is. Now, it also does ask, what are the values? Okay, so that's where we really have to do area now. So what is G of -5? Right? What is G of -5? Well, let's think about it, right? Because that's what Caleb said the minimum was at -5, right? So that means put a -5 into there. Well, that means put a -5 into here. Well, what's the area from -3 to -5? Wouldn't it be this triangle? But it's backwards, right? So how much area is that? It's a 2 by 3 triangle. 2 times 3 is 6. Half of that is 3. So what would this answer be? -3. This would be a negative area because we're going backwards. Okay? Then it wanted the maximum. We said that happened where? Where was the maximum? -3. Okay? So what's G of -3? It's the area from -3 to -3. That's going to be 0. So clearly that's less, that's more, and then we would pick up some negative area here, but not enough to offset that triangle. Okay? All right. Well, I'll tell you what. You guys do this one then. So now on H, they want to know. So take a second here, because I'm guessing, unless everybody had it and was just sitting there very quietly and not volunteering their answers. Try 56 now. Now we're going all the way from -5 to 5. Where does big H have its littlest value? And where does it have its biggest value? And then we're going to find those values. But don't worry about areas first. You can think about areas, but from -5 to 5, I'm not going to worry about this 2. Here, let me give you a hint. I'm not worrying about this 2 until I actually have to find values. Then I'll worry about the 2. But for now, where's the biggest and littlest going to be? So just look at that as the derivative graph and think about increasing and decreasing, and you can think areas a little bit and then see what you come up with. the littlest value of the big H graph. I mean, it might even help to draw a little, kind of sketch a big H graph. Well, you know what? I'm not even going to put an axis on there because I don't even care about what the values are right now. So what's the big H graph going to do? What's a big H graph got to do at the start here? It's got to go up. Until when? Till -3. And then it's got to level off, right? Actually, probably a sharp point because it kind of changes, but that doesn't really matter. Then what? It's got to go down, down, down. Until when? -1. What happens here at -1? It's still going down, isn't it? But what is that right there? Flexion point. It's going to go down, down, down some more. Now the question is, how far down? Does it go down below this point? What would determine whether it does? What area?
The area of the half circle.
That's right. Compared to this. What did we say this was? 3. While we're at it, what's this triangle here? See how this added a little bit to what our chart was before? Before we didn't really know because we were thinking slopes. Now we can add in the area piece to help us a little bit. What's this area? 4. 4 by 2 is 8. Half that is 4. What's this area here? 2 wide or 2 radius. So what is this? 4 pi, but then it'd be half that. So that's about 6 something. So doesn't that mean that this graph has to go up 3 and go down how much? 6, right? If this is an area graph, I'm going to have +3 area, and then it's going to go down 6. So it's got to go way down below where it was here at -1 then. Then what's it do?
Goes -4.
Comes back up. But how far? Right. The question is, does it come way up to here? No, because it went down how far? 6.28, and it's going to come up less than that, right? It's going to go up 4. So it's going to come up 4, which means it'll come up past this point, which doesn't really matter. So where, you see how we could get the maximum in from that then? See what I mean? See how the area helps us? It's really chart stuff, though. You're saying, wait a minute, what about that 2? What does that 2 do to this graph? This is the big H. Remember that thing when I slid it around? When I slid the left edge, what did the area graph do? Right? Here's the area graph right here. So here's the different areas. Right here. What happens to that graph when I shift this left end point? It just goes up and down. It just goes up and down, right? So, this thing I'm doing right here, this graph would just go up and down, right? So would the maximum always be here?
Yes.
No matter what that number is right there, the maximum is always going to be there. The minimum is always going to be there if you shift it up and down, right? Doesn't matter. Now, what those values are going to matter. That's where the 2 will matter, right? What those actual y values are on this graph are going to matter. But where the maximum is not going to matter. That left edge doesn't matter. So I didn't pay attention to that. Some of you are going, well, wait a minute. That's negative because it's going backwards. Doesn't matter. Doesn't matter. Okay? When I'm talking about the H graph, I'm saying this is positive, so the graph's increasing. The antiderivative graph's increasing, then decreasing, then increasing again. Okay? All right, now I want to actually find this max point that's at -3. Okay? That's going to be my max. So what's H of -3? Well, that means the area from 2 to -3. Okay, where's 2? Right here? No, 2 is right here.
2 pi minus 1/2.
Well, it'd be this triangle. And we're going backwards, right? So 2 to -3, we're going backwards. So what is that?
1/2.
I got to look. That's 1/2, but it'd be negative. Right? And then what did we say this was? 2 pi? And that'd be positive. And then this would be negative because I'm going backwards.
We're only going to -3.
Oh, we're only going to -3. You're right. Thank you. So I don't need that. So it's 2 pi minus 1/2. You're going to have to do that, right? On a graph like this, you may have to find some of these values like this. We said already you have to do these areas, but now we're putting it into an area function. Now, where's the minimum? That was the minimum. No, that was the maximum. That's the max. What's the minimum?
1.
At 1. So we need the area from 2 to 1.
-1/2.
And that's just this piece of area. And that's -1/2. So there's the minimum. Okay, there's the minimum. There's the maximum. So that problem kind of ties together all of this section 2 stuff we're talking about back here. Area function is the antiderivative. The stuff with the chart, okay? The left edge is just that plus C kind of thing. But all those chart kind of questions come into play there. All right. So that's, I wanted to make sure and talk about that one. Okay, let's move into the other page of homework. And then the one thing we haven't talked about, so we'll go over a few of those here. So let's discuss this fundamental theorem. Let's talk about parts 1 and 2 here a little bit. So the fundamental theorem of calculus. Okay, let's focus on part 2 first. Okay, that's the more useful one. The one we'll work a lot more later on. So that was this, which said we do the antiderivative, plug in the B, plug in the A. Okay, so you had a whole bunch of problems, 19 through 30. Of course, 1 through 8 were just more chart things. Okay, so that's just more of the chart kind of stuff. So later when we have work time, you can ask me if you struggle on those still, or you still have questions on those, you can ask me. But 1 through 8, did we do 9 through 16 also or not? Didn't do 9 through 16. So if you want to have some more practice, why don't you jot that down here real quick, 9 through 16 or 9 through 18 actually on page 330. Those would be good ones if you still want some of these area function chart kind of things like we just went over. That'd be a good section to revisit. Okay, if you want to take a look at those and ask me about those would be good ones to talk about. Okay, let's talk about 19 through 30. Well, I'll tell you what. You know what? I think I want to leave that for the end because I've got a few more problems to do on fundamental theorem part 2, and then of course the new thing we're going to talk about later is kind of related to that. So let's leave that for right now. Let's focus on fundamental theorem part 1. Because 48 and 49, would those be good ones to look at? 48 and 49. Okay? Those are questions that kind of deal with fundamental theorem part 1. Here's what fundamental theorem part 1 said. The derivative of the area function equals, can somebody tell me? Little f of x, right? Because what's this thing inside here? The antiderivative, right? This is just the antiderivative. So if you do the derivative of the antiderivative, they just cancel each other out, right? And the t is not a t anymore, but it's an x, right? But we had to put a t in there because we were using the x up there. So that's all that's saying. Fundamental theorem part 1 is not really that useful of a thing. It's what it is the big aha stuff, right? It's oh, wow, the area function is the antiderivative. Oh, okay. And so that's all that says. And then we went on to use that to get to this, the thing we really want, because this is the thing we can actually find areas with. Okay? So that's what fundamental theorem part 1 says. So what are some problems that would use fundamental theorem part 1? Not very much, right, that we can do with it. One simple one that I told you would probably be on there would be a problem like this. I don't think you had one of these in your homework, so let me just put it up here. So if you had, say, this problem right here, e to the, well, it'd be 2t to the third or something, some crazy thing. If I gave you that problem and said just evaluate that, what would you write down? No. That's all you would do, right? That's all you would do. The inside is saying, well, this would be the antiderivative of this with some plus c stuck on it. And then this would say, do the derivative of that. Well, the derivative of the antiderivative would just get back where you started. The c would go away. And instead of a t, you'd have an x. So if you get a problem like that, man, that would be easy. Right? That would be one easy point or two easy points or whatever it's worth. Right? It's probably all or nothing. Okay, that's all you do. The derivative and the antiderivative just gets you back to where you started with. Okay, that could be one type of problem. Another type of problem could be one like, let's see, what was 48, 49? Which one do I want to do first? Let's do 48. Okay, so 48 says, show that if big F of, or excuse me, little f of a does not equal 0, then the derivative of the integral of a to x of little f of t dt is not equal to the integral from a to x, and then in here, the derivative with respect to t of f of t dt. So show that this is not equal to this. Okay, so let's do the left side first. So what would be another name for this right here? Huh?
X.
No. Another name? Oh, no, I'm not talking about the whole side now. I'm just talking about the inside. Just the inside. What would be another name for the inside? Antiderivative. What can we put for the antiderivative of little f? How about big F? Of x plus, there'd be some c, right? There'd be some c. That's the inside. Now, you're right. You guys are saying the left side would be little f. You're right. The left side's going to be little f, right? Because isn't the left side just fundamental theorem part 1? It's a thing we just did. You're right. I agree. But I'm kind of doing it step by step because you'll see why in a minute. Now, what's the derivative of that? What's the derivative of big F? Little f. Right? And what's the derivative of the c? Goes away. Right? 0. So the left side is just little f of x. You were right. Those of you that said little f of x, you were right. Because the left side is just fundamental theorem part 1. Okay, but now this one's a little different. So what would be another name for this piece right here? Isn't that just f prime? So this is the integral from a to x of f prime of t dt. Isn't that what that is? And then what does this mean? What's the integral from a to x mean? Area, but what else? Antiderivative, right? Right? That keeps coming up over and over again. This means antiderivative. What's the antiderivative of f prime?
X.
Plus some c. Or, actually, if we use fundamental theorem part 2, couldn't we do this? Couldn't we do the antiderivative, little f, plug in an x, minus antiderivative, little f, plug in a, wouldn't it be that? It's kind of the same thing. This would just be the c right here, right? Just like we did way back in this problem back here earlier today when we did this, right? Did the antiderivative, plug in the x, plug in the pi, right? So we could do the same thing here. Okay, same thing. So are these two equal? Are those two sides equal? What's different? This one's got the plus c, this one it disappeared. Now, okay, so that would be one of the harder type problems on the quiz, but it gets to whether you really understand the notation, right? So there'll probably be some problems on there where you've got to make sure you can work with this notation. There's going to be some very straightforward, should be easy problems, the geometric areas, the fundamental theorem part 2, there'll be simple, it should be simple antiderivatives, the chart kind of stuff. That should all be easy stuff, okay? But getting into some of the notation, some of those could be a little trickier. But basically what this is saying is this. The derivative of the antiderivative is not the same as, and then how would you say this side? If this side's saying the derivative of the antiderivative, what's this side saying? Antiderivative of the derivative. Now, doesn't that seem, remember how square root of x squared or x squared and then the square root, the square root of x squared Is that the same as square root of it? Square root of x squared, is that the same as? Yeah, I got it right. Is that the same as that? Well, technically not, because this is actually that, whereas this would be that. There's kind of a domain issue that happens there. Okay? All right. Same thing goes on here. The order you do them kind of matters. Okay? Here, when you do the antiderivative, you always get a plus c, don't you? Right? When you do the antiderivative first, you get a plus c, but then when you do the derivative, the c goes away. If you do the antiderivative last, you'll have the plus c on there. See what I mean? You do the derivative, then do the antiderivative, it would be a plus c. Here, there won't be a plus c. And so they're not the same unless f of a is 0, and then, of course, then they would be the same. If c is 0, then they would be the same, right? So as long as the c is not 0, they're not the same. That's all that problem was about. Doing the derivative of the antiderivative, which is what fundamental theorem part 1 is, could we reverse that and do the antiderivative derivative? No. Okay? But again, the way you would answer that would be understanding notation. All right, let's go to 49. 49 says that big F is equal to the integral from, what is it, 0 to x. And then it's the cube root of 1 plus t squared dt. They want you to find the derivative of big F of x squared. Right? They want the derivative of that. Okay? All right, so forget this for a minute. Forget this for a minute. Just forget it, right? Big F is the antiderivative of that, right? We all get that, right? That's what that's saying. But for now, we don't need that. Just tell me what you would write that. So let's pretend this line wasn't even up here, and I gave you this and wanted you to write that down. What would you do? What would I do for this? 2x. There's going to be a 2x, right? Why is there a 2x? Because you got to kick out the derivative, right? But how does that start? How does that chain rule start? You do the derivative of the outside. Let's start there, okay? See, now, I'm not sure why this is throwing you off so much. Isn't it the same as just me asking you to do that? What's the derivative of that? You start with the outside, you leave the inside alone, times the derivative of the inside, right? That's all this is. That's all this is. Come on now. So a derivative of big F of x squared, so the derivative of big F is little f of x squared
times 2x.
Perfect. Okay. Now, what's little f in this scenario? What's little f?
Top equation, but the derivative of that.
It'd be the derivative of this. What's the derivative of this? Is it just that? That's little f, right? That's little f. Big F is the integral of little f. This is little f right there. We know that, right? Big F's the antiderivative. That's little f right in there. So what does little f of x squared mean? It means plug an x squared in to little f, right? So what do you get if you plug an x squared into this? No, what?
Cube root.
Thank you. Cube root. The cube root.
1 plus x to the 4th.
Right? You plug an x squared in to little f. This is little f. See, again, understanding the notation. Go back where it is right here, right? The area function, that's little f. That little f's in there. Okay. All right. And then times 2x, right? Now, getting started with that, I understand. I think what would make that difficult is you'd get hung up here, right? You'd get hung up with this. Don't mess with that. Do this. Do what this is saying. Do the derivative of this. That's a derivative of the outside, little f. Leave the x squared alone. times the derivative inside, 2x. So now little f of x squared means plug an x squared into little f, just like f of 3 means plug a 3 into little f. So little f of x squared means plug an x squared in to little f, which is right there. So x squared squared would be x to the 4th. That's it. You're done. That's it right there. Now, where this, and we're not going to do this, I won't ask you this. I might ask you like this, because we just did this one. But on like the packets, on the AP test, a lot of times what they do is they give you this problem. They give you that same problem, but they do it this way. They say, here's the function. We've never seen that with anything other than an x here. If there's something other than an x here, well, that's what they're saying. They're saying, oh, this is just an antiderivative, but with an x squared plugged in, right? And then they ask you to do the derivative of that. Then they say, now do the derivative of that. Well, it's the same idea. It's a derivative of the antiderivative. It's a derivative of the antiderivative. The difference is, so you might say you just get this. Well, no, you get this, but usually it's just with an x plugged in, right? Remember what we said back here? What do we do here when we do the derivative of the antiderivative? We get the same thing, except we just put x in place of t, right? Well, in this one, do the derivative of the antiderivative, same thing, except you plug x squared in place of t, and have to kick out the derivative of that. So it adds that little twist to it. That's not going to be on the quiz tomorrow. If I was going to ask anything like it, it would be worded like this, where this makes it easier to remember to kick out the 2x, right? Because you're doing the derivative of that. It looks like it's the inside. Here, that's harder to remember. As we get later in the year and we're doing our packets, we'll talk more about it when it's written this way, okay? But when it's written this way, it's probably easier to remember. Okay, so those last two, those are the tough ones. I mean, those are the ones where you really got to work with the notation and so forth. But as far as the quiz goes, a good dose of easy stuff, geometric areas, fundamental theorem part 2, which we're going to do a few more of here in a minute, and then you're going to get some more practice for tomorrow, so those should be easy. Chart stuff, that should be easy. And then, yeah, there could be some with that notation that, you know, you got to mess with a little bit, but otherwise, that's pretty much everything. Okay? All right, let's talk about fundamental theorem part 2, this guy right here. So let's look at that 19 through 30, any of those that you want to discuss. 26. Okay? Now, one big hint on 26 is I would never write that dx on top like that. I would always write it like this. Okay? I would always write it like this. Okay, so anytime you see a fraction, but a lot of times in books, a lot of different books will do this. When you have a fraction and there's just a 1 on top, they'll throw the dx up on top there, which you can, but I've told you guys all year, if I've got x divided by 4, I don't like writing it that way. I'd rather write it 1/4 x. Okay, well, it's the same thing here. Okay, so what are we supposed to do? We're supposed to do the antiderivative of 1 over x. What's the antiderivative of 1 over x? ln x. And we're going to do that from 1 to e. So we're going to plug in an e, and we're going to plug in a 1. Now, if you want to practice, or if you want to look at some basic antiderivative formulas, turn to page 333. Just turn one page over. These are the antiderivative, the basic antiderivatives we really should know. Now, I'm not going to ask you a bunch of this. They're going to be pretty basic, real basic for tomorrow. We're going to be practicing these a lot more when we get to antiderivative gateway. So, but I mean, that's a pretty basic one, 1 over x, right? Because we know the derivative of natural log x is 1 over x, so antiderivative just goes backwards, right? So we plug in an e, we plug in a 1. Now what's ln e? 1. What's ln 1? 0. So the answer to this is 1. Okay? Now you don't have to do anything with this, and it might have said something about graphing, but don't worry about it. No, it didn't say that. It said use the fundamental theorem. Here's a graph of 1 over x like this. Goes down like that. Here's 1. Here's e. We just found that little piece of area right there. Right? That's what we just found. Okay, another one. 28 is very much the same thing, by the way. 28 is just ln of x plus 3 from, what is it, -2 to 5. Right? Because ln x plus 3, the derivative of that would be 1 over x plus 3. Remember, that's how you check these. The derivative of ln x is 1 over x. The derivative of ln x plus 3 is 1 over x plus 3. So you plug in a 5, that'd be ln 8. Minus, plug in a -2, that'd be ln 1. You should know that ln 1 is 0. So ln 8. Now I would accept that. If you check it on your calculator, I think it gives you 3 ln 2. Why would it give you 3 ln 2? Because 2 cubed is 8, and it bring the 3 down. I think if you type this integral into your calculator, it'll give you 3 ln 2. Okay? But ln 8 is fine with me. Okay, and it's no calculator. This quiz tomorrow is no calculator, so you would just leave it. Just leave it like that. Okay? All right, any others on that page? I think we ought to check like one like number 20. I always say that it's just easy, basic ones, but then we mess them up. And so let's make sure we're not doing that. So I got square root of x dx. So the number one antiderivative rule you got to know is the power rule. You raise it up 1, you divide by the new power, right? Make sure we got that. So this is x to the 1/2, right? So what is the antiderivative of x to the 1/2? Well, you raise that up 1. What's that if you raise it up 1? 3 halves. Divided by, divided by 3 halves, which means times 2/3. Okay, so make sure we do that because that's probably going to be on it. Okay, make sure we can do with fractions especially. So x to the 1/2, you raise it up 1. The x to the 3 halves, you divide by 3 halves, which is the same as timesing by 2/3. And then we want to do that from 0 to 4. So that'll be 2/3, 4 to the 3 halves, minus 2/3, 0 to the 3 halves. Okay? Well, what's 4 to the 3 halves? Well, the bottom number means the root. So that'd be square root of 4 is 2, and the top number is the power. So 2 cubed is 8. How do you do 2/3 times 8? You don't get a common denominator, you just multiply straight across. That's 16/3. I still remember the headaches people had on the gateway test dealing with fractions. Okay? So we got to make sure we can do this. And then, of course, 0, that's just going to be 0. So 16/3. So this would be, now let's don't forget what we just did there. That's a square root graph, which is this. From 0 to 4, we just found that area right there. We just found that piece of area. 5 and 1/3, 16. Okay, so that's just basic fundamental theorem, part 2. Do the antiderivative, big F, plug in the B, plug in the A. I just like this right bracket notation because the reason is that tells me, okay, I've already done the antiderivative, so I take off my integral sign. I've already done my antiderivative, and now I'm just plugging in the top number, plugging in the bottom number, subtracting. Okay? All right. Anything else? Anything else out of the homework? I know we haven't covered all of them, but a lot of it was chart kind of stuff. But there might have been some that were a little different than basic chart stuff. So let's ask. This is your chance. 5.3 on the 5.3 page. Don't worry about that 61 through 65. We use those to come up with our fundamental theorem part 2. So don't worry about that for a moment. Anything else? Okay. All right, so we're going to have a 2-part homework assignment. One part is just some more fundamental theorem part 2 practice. Okay? And then, of course, just review for the quiz. Go back and rewatch this video, or just thinking about these things that we went through here, trying to summarize and put all this stuff together. These are the things we kind of emphasized today. Those are the main things you want to make sure you're clear about. I think we've pretty much hit on all of the different ideas, for the quiz. So let's take a look at an example. Now this is going to be Fundamental Theorem Part 2 kind of stuff, but it's going to be but stuff that won't be on the quiz. This is just goes a little beyond where we're at right now to be able to do. Okay, but tomorrow after the quiz, there's going to be, because you're going to have some time after the quiz, and you're going to be working on some problems like this. Okay, so hang on here a second. All right. So we're going to talk about antiderivative. So this would be just something to jot down in your notes here real quick. So we're talking about antiderivatives. Okay, so we have our basic antiderivative. Okay, just kind of derivatives in reverse. The power rule, sine, cosine. E to the x is really easy because it's its own antiderivative, right? That kind of thing. What about, I guess before I do this other thing, what about sine 2x? What would be the antiderivative of sine 2x? Well, first, what's the antiderivative of sine? Because it'd be negative, right? And the inside always stays the same, right, when you do a derivative? Won't there be a 1/2 out here? Remember when we did that? There'll be a 1/2 out. Now, why is there a 1/2 out there? When you do the derivative, you'll have to kick out a 2, right? Remember, an antiderivative can be checked by just doing the derivative. So we can do the derivative in this. You say, okay, derivative cosine is negative sine. The negative will cancel that negative. We'll have to kick out a 2, but there's no 2 kicked out here. So there must be a 1/2 out there, which would have offset that. Now, not going to be a big deal tomorrow. There could be a simple one like that with a 2 in there or something you can kick out. But, right, so those are just kind of your basic antiderivative. But let's visit more of this thing about something on the inside. If there's other stuff on the inside, right, like an x squared, for example. Okay, now if you happen to have your calculators handy, if you would put in this into your calculator. Somebody's, well, I've got a calculator handy right here. Let's do it. So let's put in the integral. Now, notice there's an integral with the little boxes here, and then there's also an integral without the boxes. Okay? Well, what that is just the antiderivative symbol. That's the symbol for just doing the antiderivative. Not finding any area, just doing the antiderivative. Now, you're not going to have that symbol on your quiz tomorrow, but that's the symbol that just says, hey, just do the antiderivative. We're not even worried about area here at all. Just give me the antiderivative. Okay? Well, if I type that in, what did it just tell me? Yeah, there isn't one. There isn't one, which is weird because you never get that with derivatives. There's always a derivative. You can always do a derivative because we have the rules for all the different situations. But remember, so it kind of makes sense, though, because for there to be an antiderivative means there had to have been some function that when you do the derivative gives you that. Well, any function has a derivative, but that doesn't mean it gives you all the possible other types of functions there are, so that you can always go backwards. So some functions don't have an antiderivative. Okay? Now, you could probably, oops. I need to grab. There we go. I'll bet if I put a 2x in front of here, you'd be able to tell me what the antiderivative is. What do you think the antiderivative is going to be? Take a guess. Is it negative or not?
Oh.
Wouldn't it just be sine of plus some c? Let's test it. What's the derivative of sine of x squared? Cosine of x squared times 2x, because we have to kick out a 2x. So what that means is, since we know the derivative on one of these will be kicking out that, doesn't that mean when we work backwards, the thing that's getting kicked out is going to have to be setting out there? You see what I mean? The thing that's going to get kicked out had better be setting right there. Okay? Well, it's not always going to be setting right there. So if it's not, like it wasn't here, there might not be an antiderivative. Okay? In this case, it was setting right there. So if it's setting right there just perfectly, those will be easy. Now, sometimes only parts of it will be setting right there, and then we've got to be able to deal with that. So here's what this looks like. And this is a method called, so let me put a 2x, oops. So let's change this, let's put a 2x right in there, okay? And this is called U substitution, what I'm going to do right here, okay? And this is kind of the chain rule in reverse, when there's stuff on the inside. Okay, now this one was easy, this 2 on the inside, we just knew we'd kick out a 1/2, that was easy. But when it's x squared or something like that, that's not as easy. So here's what we do. We let u equal the inside. Now there'll be other times we let u equal other stuff, and we'll spend several days practicing this. But for right now, all you need to write down is let u equal the inside stuff. Just let u equal the inside stuff. Okay? Now, we're going to do the derivative of u. Now, we could write u prime, but actually it's going to be more to our benefit to write du over dx. Okay, instead of u prime. So we're going to do the derivative of that. Okay, so what's the derivative of u? 2x. Now, of course, you can see where we're going with this because we know when we do the chain rule, we do the derivative of the inside. Well, what I just let u equal? I let u be the inside stuff. I did the derivative of u. I'm doing the derivative of the inside. I'm writing it right there. But this is called u substitution. So what we're going to do now, I'll do it in blue, we're going to write a new integral, and we're going to substitute out all the x's, and we're going to replace them with equivalent u's. Okay? We're in the middle of basketball, well, not the end of basketball season here, so we'll think of it like basketball. In basketball, you have substitutions, right? We're going to substitute out all the x players and put their substitutes in. So, right there, I could put what in that place? What can I put in place of the x squared? U, right? Now, I still have the cosine, right? So I have cosine u, right? So that I've substituted out right there. That has been substituted out and replaced with a cosine u. Now, this dx, how am I going to get that out of there? Oh, you know what? Let's come back to this. Now, we've never done this before, but it's actually legal to do. We can take this dx and move it over to here. So I'm going to do that. No, you'll see why it's, this is a pretty easy one because we already know the answer, but this will be, it'll be much easier and there'll be a lot of problems we would never be able to do if we didn't do this. So what I've done here is I've moved the x over there so the x's are with the x's, the u's are with the u's, right? So, so du is the same as 2x dx. So look at this. 2x dx right there. I could substitute that out and put what in its place? Du. Look what I just did. I turned this more complicated looking integral into this really simple integral. See what I mean? Now all we have to do is the antiderivative of this. And notice everything matches because remember this means with respect to. So we're doing the antiderivative with respect to u. What's the antiderivative of cosine? Is it negative or positive? It's just sine u plus See? And now at the very end, we're going to sub them back out. We'll take the U's back out and put what in place of the U? Right here, U is equal to x squared, and look what we got. Sine of x squared. Which, of course, we knew what that was the answer. Now let's just go over what just happened. We had an integral that we did not know how to do an antiderivative of, right? We were being asked, that's what this integral symbol without any numbers on it means, antiderivative, okay? You're not going to see that in the quiz, don't worry. That just means do the antiderivative, okay? Well, we don't know how to do that. That 2x is messing things up. It's got an x squared inside or whatever. So we do this thing called U substitution, which we typically use whenever there's stuff on the inside. When there's messy stuff on the inside, this is what we do. So we let U be the inside stuff. We did the derivative of it. We flipped that x over there. And then we just wrote a new integral. And we subbed out all the x's and we put u's in their place. So that became cosine u. Those two things together were the du. And we traded this complicated integral for an easier integral. Now we can do the antiderivative. And then we put that back in. And then we can check it. And sure enough, we already did. But the derivative of that is that right there. That's called U substitution. So there's a few homework problems in the book, just like 4 of them, so, but they kind of lead you through those steps. Now, you don't have to even do those if you don't want to for tomorrow. You can do them. They can be part of Wednesday's homework after you get over the quiz. Okay? All right. So in that LH packet, so let's talk about basically your homework. 3 through 36 multiples of 3. You can do more than that, but that's just that's probably enough. So like 3, 6, 9, 12, right? So it's like 12 problems. Those are like 19 through 30. Those are fundamental theorem part 2 problems. Okay? Fundamental theorem part 2. Right? So that's that LH packet. It's in the packet. Okay? So they're just like 19 through 30 on today's homework work. Okay? So like we did right back here. This kind of stuff. Okay? So it's just a little more practice. Now again, that's a part of the quiz. That's just one part of the quiz. That's this part down here. Right? So it's just a few additional problems. But the rest of the review for the quiz was the homework, all the stuff we talked about today. So there's no more problems. Although I did tell you, what were those other ones I told you would be good to do? I said 9 through 18 in section 5.3 weren't bad. Was that 5.3? Yeah, 9 through 18. Those are just some more chart ones. I mean, to be honest, I'm not going to check this tomorrow. I mean, so that's just up to you. Okay, so those are kind of some chart ones. Because we did 35 through 38. We did that section, and we did 55 through 58, which were some chart ones again. I mean, so we had those. So here's just some more with that. So that gives you some help on those kind of things. All right, and then if you feel good about that, you want to get a head start. 1 through 9 odd. This is section 5.4 in the book. That is not on the quiz. Okay, the stuff below the line there, that is not on the quiz. So 1 through 9 on. Then I'm going to add more to that for Wednesday. So if you want to get a head start on thinking about this U substitution thing we just talked about, but again, it's just a way of doing antiderivatives. Which to do fundamental theorem part 2, that's what you have to do. You have to be able to do antiderivatives.
So 1 through 9 is not required.
So that's not required for tomorrow. That's not on the quiz. Okay. So those would be a couple of things I would say, and then review, just these ideas of what we did today. And so you got not much time, I guess. So that, I'm sorry, what page is that on the LH? That would be that, it's on your assignment sheet, page 298. So on the LH, that's page 298, okay, in the LH packet. It's written on your assignment sheet, but